Okay, this video is regarding chapter 6, which is about energy. Okay, so as usual, when I start with a topic, I'll try to define it. Now, the thing is, energy is kind of a funny topic in that most people think that they know what energy is. Energy is a term that's used in the vernacular all the time. Yet I claim that really nobody has any idea what energy actually is. Even though we use it all the time, we even have a Department of Energy in the United States government. We have energy drinks. We have, if I feel low on energy, I'll have some caffeine. But what really is energy? We are pressed to try to give a definition for it. Most people cannot. In fact, many professional scientists don't even know really what energy is. And so the nature or the subject of this chapter is energy. And so I will give you what the definition of energy is, and then how we can calculate energy in different ways. All right. So first of all, we need to motivate why we even need a concept of energy. We walk into this chapter, we should be quite confident right now. We have Newton's second law, we have Newton's laws, and we understand how forces cause objects to accelerate, and that links us from forces to kinematics, and vice versa. If something accelerates, we know there must have been a force applied to it. The concept of a force is the why, or the reason why we have kinematics. Galileo did not know that. And so we seem to have the ability to solve any kind of physics problem. At least we think we do. However, everything's great until it's not. All right. So when might we have problems applying Newton's laws of motion? Well, let's start off by looking at a problem. Let's just take two bodies with an interaction. So we'll say we have a planet, we're familiar with that, and say a moon. All right. And so we have a center distance, d, and we know that we can solve this problem. This is a two-body problem. So these are two masses, or we'll say two objects. I mean, they could be charged obviously with electrostatic force, but two objects with a force of interaction. Okay, we can solve this problem analytically. That means we can get a closed form solution. If I were to say that, I were to call anything dealing with the planet 1 and say the moon 2, I can talk about, x2. I can talk about, let's say, the velocity 2. I can have variables that are entirely with respect to, say, the moon. I can also have variables that are entirely with respect to the planet. And I can actually solve equations of motion for each one of these. Equations of motion are essentially the equations that govern how the bodies move in time. So no problem. That's two bodies. Doesn't surprise us. Well, how about putting in the third body? All right. So again, analytically means I can solve it with pencil and paper. Closed form solution. Well, let's throw in a third body. So let's say we have planet, a moon, we'll call it moon 1 and moon 2. Planet with 2 moons. Again, this doesn't look like one. So we have an interaction between the planet and the moon, moon 1. We have an interaction between the planet and moon 2. We have an interaction between moon 1 and moon 2. We have a 3-way interaction. Well, this is the famous 3-body problem. And why is it famous? Because the 3-body problem cannot be solved analytically. We think we have it all figured out, yet we can't even solve a 3-body problem. The only problems we can solve analytically with pencil and paper have closed form solutions is for a 2-body problem. 3 bodies, 4 bodies, anything bigger than 2-body problem, we cannot solve analytically with Newton's laws. The reason being there's too many equations, not enough variables. So we simply we need to we have n variables and n equations. So we cannot solve this problem analytically. We cannot deal with pencil and paper. Cannot deal with 4 bodies or any 3 or more. Basically, you cannot solve this analytically. So we're already in trouble. Well, one could say, oh well, you could write a computer program to do it. So you can write a computer program to essentially, let's say, at every single step, you take a time step. Every step, your computer program does what? Well, your computer program knows that there's a configuration. We'll figure out what the interactions are at any given time and figure out how to adjust the movement of the planet, of the 3 bodies. And then you go to the next time step interaction, figure out where the bodies are now, how they interact. You can kind of step through time. And so every single instant of time, you'd have to perform 3 interactions. Well, that could work. You can use something called like an Euler method is a good example of how you could write a computer program. Named after Leonard Euler. So, and in fact, I could write a C program to do this in about 20 minutes. In fact, I don't even really need a C program. I can actually do this in Excel. So, okay, fine. Well, what happens if I have 4 bodies? Okay, so I have this computer program. Well, let's try to do 4 bodies. Well, how many interactions do I have now? Well, I have body 1, 2, 3, 4. So I'll have interaction between 1 and 4, 2 and 4, 3 and 4. Let's see. Let me do 1 with 2, 1 with 3, 1 with 4, 2 with 3, 2 with 4, and 3 with 4. How many is that? 1, 2, 3, 4, 5, 6. Okay, so I saw with 3 bodies, I had 3 interactions. Here with 4 bodies, I have 6 interactions. What about 5 bodies? Well, 1 with 5, 2 with 5, 3 with 5, 4 with 5. I'm sorry, I keep messing that up. Again, 1 with 2, 1 with 3, 1 with 4, 1 with 5, 2 with 3, 2 with 4, 2 with 5, 3 with 4, 3 with 5, and 4 with 5. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, it turns out that if I were to consider n bodies with their interactions, it comes out to be n times n minus 1 all over 2. So if I look at, say, for instance, 4 bodies, I have 4 times 3 is 12, divided by 2 is 6. 5 bodies, 5 times 4 is 20, divided by 2 is 10. And so, for not too many bodies, every single time I have an interaction, every time I take a time step, for instance, for 5 bodies, I have to do 10 calculations in my code. Well, let's say if I have, let's say 10 bodies, 10 times 9 is 90 divided by 2, 45 interactions. Every single time I take a time step of 10 bodies, I have to do 45 interactions. And so every single time, 45 calculations. Well, this number gets pretty big. And in fact, for a large enough n, this one kind of becomes negligible. So this kind of goes like n squared over 2. 100 bodies, 100 squared is 10,000 divided by 2, 5,000 interactions per 100 bodies. Well, let's be realistic now. Let's take a volume of gas. How many, if I'm trying to go in Newton's laws and I'm trying to model, gas molecules, how many gas molecules are there? Well, there's like 10 to the 21st. That's 1 with 21 zeros after it. 10 to the 21st gas molecules and per cubic volume, per cubic meter. I square that, that's 10 to the 42. I don't care if you have a quantum computer, you can't do that. So one way or the other, either sooner or later, you're going to get beaten by population alone. It's just going to be too hard to apply Newton's laws. What might be another reason why Newton's laws are too hard to apply? Well, let's look at Newton's second law again. Sum of all forces, mass times acceleration, again on a system. Well, I have no problem finding the mass of a system, and kinematics is not too hard of a deal either. I can understand the acceleration of a body. The problem you're going to have is left-hand side. How easy is it really, in most general case, to resolve the forces? Resolving forces is oftentimes very difficult to do. Can you even do it? So essentially, it's not too hard. In fact, it's scarily easy to actually make a problem that's too hard to do Newton's second law or to do Newton's laws. So we came, into this chapter with great confidence. We have this, Newton's laws, and we're basically, feel like we can solve any problem. And then we find out we can't even solve a 3-body problem analytically. And we come to find out that, well, it's not too hard to come up with a situation where you really can't even resolve the forces. And if you get a big enough set of problems, you can't do Newton's laws for a gas, even a small gas. So what do? We have to kind of go back to the drawing board now. I mean, it's kind of deflating. We thought we knew everything, but we kind of are stuck. So when you have a difficult problem, one that's almost seems insurmountable, sometimes what you have to do is kind of go back to the drawing board. Kind of go back to the first principle. Let's go back to the first day of class, the first lecture. And let's ask ourselves why we're here. Why is it? What are we trying to do? Well, what we're trying to do is we have a system at time in state 1 at time t1, okay? And we can characterize this system. Okay, we can characterize the system. We know what's going on at time t1. The question is, we really would like to find out what's happening at a later time. So we want to predict the system at state 2, at time t2 later. Now, we are spoiled right now with Newton's laws, because not only can we predict what's going to happen in the system in a future time, we actually know exactly how the particles in that system are even going to evolve. We know how their equations of motion, how they're going to get from state 1 to state 2. Not only can we characterize state 2 in the future, we actually know how the variables, how the whole system will unfold. But as we found out, it's very easy to come to a situation where we can't apply Newton's laws. So how can I say anything about state 2? How can I, and again, what's physics about? Basically physics is about predicting the future. That's what we're all about here. We know our system at state state 1 at time t1. We want to understand what the system is doing at a later time t2. So how do we go about doing this? What in any way can we do? All right, so I'm going to take a deviation at this point, and I'm going to follow an idea that I got from Richard Feynman. And so, kind of give you an idea if you haven't heard of Richard Feynman before. He's the greatest practitioner of physics since Einstein. So, in fact, a good set of lectures, if you go on in physics, you can buy these Amazon or Barnes and Noble, but probably the greatest set of lectures written ever is the Feynman Lectures on Physics. So, as an aside, Feynman was a professor at the California Institute of Technology, or Caltech. And right around 1960, the Caltech Department of Physics, the physics department, kind of felt like that all the great things happening in the 20th century are not being captured. Physics being taught to the freshmen and sophomores, physics majors at Caltech, they weren't getting the latest information. What's developments happen in relativity and quantum theory and atomic physics. And so what they wanted is they wanted somebody who is an expert to restructure the physics curriculum. And so Richard Feynman only ever taught graduate level courses. They thought that they approached him about it, that they wanted him to go do this, and they kind of thought that he was going to reject it and say, I don't have time for this. And to their great surprise, he actually was extremely happy to do it. In fact, in between 1961 and 1963, he reformulated the freshman sophomore physics curriculum at Caltech. In fact, these Feynman lectures are so great that all physics textbooks that really have been written since then, I don't care if they're calculus-based books like Holliday and Resnick, or Eisberg and Resnick, or Tipler, or Sears and Szymanski, or whatever the books are, or the college physics books like OpenStax or Cutnell Johnson, all of them have really leveraged off of this brilliant work. Okay, so I've read the Feynman lectures come in 3 volumes. I've read them at least a couple of times. And so what I try to do is I try to use ideas I learned from his lectures to try to bring those ideas to you. So when Feynman talked about energy, he had a kind of a funny way of doing it, and I'm going to kind of borrow his way. Now, what Feynman did is he focused on toy blocks owned by Dennis the Menace. Now, you probably are saying who? And in fact, I was born in 1971, and Feynman wrote, did these lectures 8 to 10 years before I was born. And honestly, Dennis the Menace is a comic strip character. I hardly know who he is, right? So I'm kind of reformulating. I'm gonna kind of use, I'm gonna pretend that we are pre-COVID-19. That in my little universe, I'm gonna pretend that we are actually meeting face to face in the classroom, and that restaurants are open. And I'm gonna pick something that I would expect you not to actually have on your person coming into my class. And again, I'm apologize ahead of time because this is a very silly example, but it's an example that I'm using to kind of get the idea across and how we're going to develop the concept the rest of this class. Okay, so in my example, I involve the restaurant or video arcade place called Chuck E. Cheese. All right. Now this example worked more easily when my kids were young. Let's pretend for a moment that I take my kids to Chuck E. Cheese. So again, for those of you who weren't born and raised in the United States, Chuck E. Cheese is a video arcade for kids, and essentially you buy these Chuck E. Cheese game tokens, and you utilize these game tokens to operate the video games. And you can have pizza and other stuff there. It's like heaven for kids, right? Let's imagine that I took my kids to Chuck E. Cheese over the weekend, and I come back home and I realize, to my chagrin, that I have exactly in my pocket. I have exactly 100 of these Chuck E. Cheese game tokens. Okay, and I have 100 of them. And I ask myself, well, what am I going to do with these? And I realized, you know what I know I can do? I could go and hand them out to my students. So let's say there's 25 of you. So let's say at beginning of class, I'm going to hand these out to you. And each one of you gets like 4 of these tokens. And so imagine for a moment, I have my system, which is the classroom. There's my system. My system is all of you, me, all your stuff. Whatever you carry on you or whatever you're wearing or whatever, and 100 game tokens. Okay, that's my system. And I can look at, I can say time T1, the class starts at exactly 7 p.m. And so I look at my system at 7 p.m. I look around and I see my configuration of my system. Now I have really no idea what's going to happen from 7 p.m. and onward. Basically, some of you might decide, I'm going to go take out my laptop. I'm going to put my book away, or take out my book, or take out a notebook, or I'm going to put on my sweater, or take off my sweater, or my sweatshirt, or I don't like this seat. I'm going to move into another seat. And in fact, you may actually exchange, the game tokens, or you might put them in your pocket, or your purse, or what have you. Okay, so there is, as I'm teaching, starting at 7 p.m., the system is evolving. And then I say later on, I say at 8 p.m., T2 is 8 p.m., and I say, stop. I turn around and I want to get a count of all the game tokens. And let's say we count them all out, and say we find out initially that we only have 80. And I'm like, 80? I thought we had 100. And then we look around, and some people may still have some in their purse, or maybe in their pockets, or maybe they drop them on the floor or underneath their notebook. But eventually we find all 100 of the game tokens. So life is good. At 7 o'clock, we had 100 game tokens, and at 8 o'clock, we have 100 game tokens. So we found out that we actually have 100. Now, what am I doing here? Well, I'm trying to characterize my system. I'm trying to say something about the system at a future time. So in a silly example, I can say, in this classroom, in my system, at T1 equals 7 p.m., I know I have 100 Chuck E. Cheese game tokens. And at a future time, my system at T2 is 8 p.m. I have no idea exactly what the configuration is going to be, but I can say at least one thing about the future. And that is, I have 100 Chuck E. Cheese game tokens in the classroom. And so what I've actually have done in this very silly example, and again, there's a reason, there's in the analogy, there's a reason why we initially lost some tokens. In this silly example, I have defined a conservation principle. I have the conservation of Chuck E. Cheese game tokens. All right, silly example. But it's at least, I know that at both frames of time, that I can say something about the future. I mean, as silly as it may be. Now you might say, well, there's a lot of conservation principles in the world. I mean, like, I'll give you another example. A few years ago, my wife was making cupcakes, and my son was going to bring them to school, and she tells me at 9 p.m., Mark, there's 24 cupcakes. There better be 24 cupcakes in the morning. Essentially, enforcing a conservation of cupcakes, or for instance, the study of financial accountancy. Essentially, what is that? That's a conservation of money. Essentially, if you're running a business, you should not have money magically appearing in your bank account. You should also not have money, mysteriously disappearing in your bank account. You should be able to account for every penny that goes in and goes out. So you might say to me, well, so what? There's so many examples in real life of these, what you call conservation principles. Why do I care? Well, in physics, conservation principles are very rare. And you have to look far and wide to see anything that is conserved from the state, basically for your system from one state to another. So physicists look far and wide. Is there anything that is conserved? I mean, I can't do Newton's laws right now. The system's too difficult. I cannot do Newton's law. I cannot do analysis using Newton's laws. So what do I do? Well, physicists looked far and wide, and they did find something that was conserved, and it's called energy. And so energy is the following. I ask you, what is energy? All of this is the following. Energy is a scalar number that you calculate in the system. At a time t1, you let your system evolve. To a later state, 2 at time t2, and when you calculate this number again, it is the same. That's all energy is. It is just a number. Scalar value is a scalar, it's just a number. You calculate it in your system at a time t1. You let the system evolve. You calculate this number again at a later time t2, and lo and behold, that number is the same. That is all energy is. So people all, we have all this thing, energy drinks, everything else. Energy really, in a theoretical sense, is just a number that happens to be conserved by the universe for whatever reason. And that is our fourth of 4 laws of physics that govern mechanics. We call this the conservation of energy. So total energy is always the same. So the total energy in a system is always the same. We call this the conservation of energy. So mechanics is governed by 4 laws or principles. Newton's first law. Newton's second law. Newton's third law. And the conservation of energy. So as we are developing mechanics, we're on chapter 6 And we have all of the laws of physics. And it's rest of what we're doing in mechanics is just applying them. All the laws of physics. So now it's interesting in that, you know, energy, you're going to find out it takes many forms. It actually turns out that even though energy seemed to be like a life preserver to kind of allow us to do physics, physicists actually prefer to work in energy. We actually have an entire field of mechanics that entirely depends on energy. You actually get the laws, the equations of motion by applying certain differential equations to the energy. So essentially, we have Lagrangian mechanics, and Hamiltonian mechanics. They are energy-based. So they are the more pure way of doing physics. Literally, you have everything formulated in terms of energy. And from this, you can actually, there's actually a recipe to get you the equation of motion. It always works, and it's easier to apply. You can apply it in much more complicated situations, which might be too hard for Newton's laws. And so, you know, you see Lagrangian Hamiltonian mechanics. I mean, again, this is one of those times as a physics major when I really fell in love with physics, because this is some of the most beautiful theories you can ever imagine. It's very, very beautiful, very powerful. So literally, this is the most advanced and most I would say pure way to actually do physics with, you know, basically with these pure energy theories. All right. So first of all, though, I'm going to show a little video, because one of the things we're going to see is that energy takes many forms. Now, I took this video of my son at the Pro Museum. So again, the Pro Museum, it's over in Dallas. I mean, if you haven't been there, the Pro Museum of Nature and Science, definitely a place to go. And it was founded by H. Ross Perot. And he ran for president of the United States back in the late 80s. But he was also a very successful billionaire. And, you know, out of the big families live in Texas, richest families in Texas are like the Perots, the Bushes, and the Basses, right? And so Perot, you know, he's definitely a friend of science. Unfortunately, he passed away in 2019. But yeah, he basically formed this beautiful museum. And so this museum, the fourth floor is entirely a physics floor. So I'm going to show you an energy machine that I had my son operate. And all I really want to do is kind of show you how, you know, all the different forms. Here's a simple little cyclical machine, and yet has all these different forms of energy. So let me see if I can change here, share the screen, and go to. No, maybe not. Hang on one second. Let me try something else. All right. Let me. All right. Let's see if I can try to make this work. Well, I thought I can do it. Oh well, all right. I guess I won't be doing that. All right, so let me exit full screen for a sec here. Hang on one second. Let me see if this actually works. No, that didn't work. All right. No. All right. Well, we'll just move on. I have to figure out how to do that in the future, I guess. All right. So never mind. All right. So the idea here is that many many books, including this book, and and many books actually will start off by introducing energy to you, but they do it in a way where they kind of assume you have familiarity with energy already, and that everybody's talking about energy, so it must be important. Well, there's a number of different things that everybody talks about that isn't necessarily important, right? You think of reality television, for instance. Everybody talks about it, but I wouldn't necessarily call it important. So a lot of books, a lot of chapters will start off by saying, well, here's all these different kinds of energy. You have work, you have potential energy. The reality is, as a scientist, you need to prove everything, as you study it. And you need to question everything, even things that people take for granted. You need to question. And as silly as it may sound, you need to question the importance of energy. Just because people tell me it's important, is it really important? Why do I care that I can calculate work and potential energy? Well, what makes energy important is it is conserved. It is a conserved quantity, and it is a law of the universe, the conservation of energy. People who write books, that talk about energy, energy, the very first thing that they should have in their chapters, as exactly as I taught it, is to motivate why you want to talk about energy in the first place, because it is a conserved quantity. And then once you have convinced everybody of the importance of energy, then we can start talking about the different forms of energy. All right, so again, that's the way I think things should actually be approached. So, as your book does, your book starts off talking about the first form of energy called work. Now, work is a natural extension of what we've been talking about so far. We've been talking about forces, and we've been talking about displacements and kinematics. So work is a natural, as a natural first energy. However, before we start talking about work, we need to talk about how to multiply vectors. Okay, so far I've been telling you all about how to add and subtract vectors. I have told you how to multiply a vector by a scalar, but I've held off on multiplying vectors until we absolutely needed to, because vector multiplication is very different than anything you've seen before. Okay, so let's go into, and it's going to be important when we talk about work. So there are two ways to multiply vectors. Okay, two ways. We have what's called a scalar product, and we have what is called a vector product. Okay, scalar product, vector product. Now, a scalar product is basically vector times vector equals a scalar. The vector product is a vector times a vector equals a vector, but probably not the kind of vector you may be thinking. Now, generally speaking, we like to think of, well, you know, real number plus real number gives you real number, right? It looks kind of weird to say that vector times a vector gives you a scalar. All right, but that's what's important to work. So we refer to this, first of all, as a scalar product. So I'm going to draw two vectors, A and B. I'm going to kind of imagine that they're kind of connected together as an angle theta between them. So I have A and I have B. There's two vectors in space, and I'm going to put them so that they're kind of like, I can kind of show you how there's an angle between the two. Vector A in space, vector B in space, and here's an angle theta between the two. Now, we oftentimes refer to this as a dot product. You use the dot form of multiplication. So you would say A dot B. You would literally pronounce this as A dot B, called the dot product. Okay, A dot B is the magnitude of A, just the length of A, I'm taking the hat off, times the magnitude of B, times the cosine of the angle between the two. So literally, the magnitude of A is a scalar, the magnitude of B is a scalar, and of course the cosine of the angle is a scalar. And so one example of a dot product, as I'm about to talk to you about, is work. Work is an energy, work is a dot product. Okay, so one way, vector times a vector gives you a scalar. A dot B, two vectors going in. We pronounce it A dot B, we use the dot symbol for multiplication. A dot B is the magnitude of A, the length of vector A, times the magnitude of B, the length of vector B, times the cosine of the angle between them. Okay, so we're going to use that right now, but I'm going to introduce the vector product briefly. We're going to put it on the shelf. We'll talk about the vector product later when we talk about angular momentum and torque. And in physics too, we'll find out that the the vector product is so important. It's actually part of a fundamental force. Everywhere you have magnetism, you have this vector product. So let's talk about the vector product briefly. And again, we're gonna put this on the back burner, but I want to at least introduce this. That's one way multiplying vectors is the dot product. The vector product we actually will use was the crossbuck form of multiplication. We literally will call this a cross product. And when I write this, I would literally write this as A cross B. Okay, let me draw my vectors again. So I got A and B, and the angle between them is theta. Now, A cross B is the magnitude of A times the magnitude of B times the sine of the angle between them in a direction perpendicular to the plane formed by A and B. According to the right-hand rule. Okay, so what does all this mean? Well, I can understand right off the bat how to find a magnitude. Magnitude of A times magnitude of B times sine of theta. That's nothing but a magnitude. Now, as I read this more carefully, in a direction perpendicular to the plane formed by A and B. Well, you look at A and B as written in this on this whiteboard. They're in the plane of the whiteboard as I've written it. That means that whatever the cross product is perpendicular to that plane. It's either straight out of the board or straight into the board. Which is it? Well, that's determined by the right-hand rule. Now pay close attention. The right-hand rule, you want to read the product from left to right. I take my right hand. I line my fingers up with the first vector, A. I cross my fingers into the second vector, B. Where my thumb points is where that cross product vector goes. A cross B with my right hand, my thumb is pointing into the board. A cross B is into the board. Typically, when you see a vector that's into the board, you'll kind of like you imagine an arrow. You know, if you're shooting an arrow, the tail feathers behind the arrow is if the arrow is going away from you. If the arrow is coming at you, the point is coming to you. So I would actually draw tail feathers here as the arrow is going into the board. So A cross B, my thumb points into the board. What about B cross A? What about B? So A cross B is into the board. What about B cross A? Well, again, I will, if I do B cross A, I again read left to right. I line my fingers up with the first vector. I read B first. So I put my fingers along the first vector and I curl my fingers in the direction of A. So go in the first vector, I curl in the direction of A. And my thumb is pointing outward. So B cross A, thumb points outward, is out of the board. This takes a little getting used to. A cross B, again, I line my fingers up with A. I curl my fingers toward B, and my thumb naturally, again, my right hand, my thumb naturally points into the board. B cross A, the other direction. I read left to right. B, I line my fingers up at B first, curling them toward the second vector A, and my thumb points out of the board. So what's interesting here is that, you know, we take the commutative property of multiplication as a given with real numbers. You know, in multiplication, we talk about the commutative property. We always say that, you know, A times B equals B times A, right? You know, for real numbers. So for real numbers, the commutative property of multiplication is always true. A times B is B times A. However, for higher math, for higher level, you know, for mathematical objects, in higher math, like vectors and matrices, the commutative property of multiplication is almost never true. I have two matrices, A and B, for matrices. A times B, again, this goes even higher up than vectors, but we consider matrices. A times B is almost never B times A. For cross products are actually called anti-commutative. So cross products are anti-commutative. What that means is that A cross B is actually negative B cross A. So clearly, by almost invariably, cross products fail commutativity. And this might be your first example of that in your scientific career. All right, and so again, we have a completely different kind of multiplication here. Now I'm going to put cross products on the shelf right now. Again, cross products will be very important when we talk about rotations. You know, for instance, when we talk about angular momentum, we talk about torque, and we go to physics 2, the magnetic force is a cross product. So every single place where you have magnetism, the fundamental force law of electromagnetic theory has a cross product in it. So you might ask, is this important? Well, yeah, if you're going to talk about fundamental force of electromagnetic theory, you're going to talk about cross products. So again, cross products will not go away, but we're going to put them on the shelf for right now because I want to talk about work. I want to talk about energy. So we're going to talk about right now the concept of work. This is our first form of energy, work. Okay. So in general, work is defined as the dot product of a force vector and a displacement vector. So if I imagine, for instance, that, you know, I have an object that's displacing, let's say I have maybe like a sled. So I have a situation where I have a sled on ice. So there's no friction. This is just, you know, ice, no friction. And let's say somebody's pulling this, maybe a dog or maybe a human. You know, here's the horizontal, and maybe there's a rope. And again, what's nice about ropes is that you can actually direct force via tension. Let's say somebody is applying a force. Here's your force vector, and the sled is displacing, you know, let's say along the horizontal. And let's say there's an angle theta. Well, what work is being done by this process? Well, the work would be the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Again, D stands for, in this case, displacement. F is applied force. All right, what will be the units of this then? Well, F times D. So what are the units of work? Well, I have newtons times meters, or kilograms meters per second squared times meters, or kilograms meters squared per seconds squared. when we see this, let me write this a little higher. So the units of work is newtons times meters, newtons times meters. Or what's a newton? Well, newton's a kilogram meters per second squared. So putting it all together, I have kilogram meters squared per second squared. Again, as I said in the first class, first lecture, units are always some form of mass, time, and distance, right? And so we see this unit, sets of units together. The unit of energy in the SI is called the joule. And it's oftentimes given by the symbol capital J for joule. So in SI units, we have joules. In the English units, we have calories. All right, so we have now an energy. Now, what's nice about energies is that they are scalars. We've been working with all these vectors and all the involved calculations that come into play with vectors. Well, what's nice about scalars is that our energy is a scalar. You just add them up. They're just numbers. All right, and so let's get our feet wet here and work out some problems. All right, and so let's see here. Do OpenStax. So again, we're one chapter off. In our book, we're in chapter 6. In OpenStax, we'd already be on chapter 7. Okay, so don't let this fool you. So we're in OpenStax again, 7.2. Okay, we're gonna do some work. A 75 kilogram person. Climb stairs. Gaining 2.50 meters. In height. Find the work done to accomplish this task. All right. Okay, so the question is, we have a person who's basically pulling up his own body weight. So imagine this person has a mass. Well, this person is fighting against gravity, fighting against weight. So there's gonna be a force going down, mg. And this person is applying a force F. And the question is, well, what is that force? Can I characterize that force first and foremost? Well, let's see. We're assuming that this person is climbing at a constant velocity. So let's assume that the person climbs at a constant velocity. So when I apply Newton's second law, sum of all forces in the y direction, well, I have this force that this person is applying to lift himself up or herself. And again, the only other force in this problem is the weight. And that's going to equal mass times acceleration. But I said that I'm assuming zero velocity, or I'm assuming constant velocity, I'm sorry. So we're assuming the acceleration is zero. So the magnitude of whatever this F is mg. Okay, and so this person is going to be climbing stairs by applying a force capital F. Now the question is, and the displacement is aligned with the force. They are aligned. the person is climbing straight up. He's applying a force upward, and the displacement is also upward. It means the angle between the force vector and the displacement vector is 0. So what is the work being done? The work is the force dot product with the displacement. Okay, and so we know that these two are aligned. So again, it's going to be the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the two vectors, and the cosine, that angle is 0. Cosine of 0 is 1. So it's just F times D in this case. All right, and so we can calculate that. We're told that the this person, well, we know that this person has a mass of 75 kilograms. So we happen to know that the magnitude of the force is mg. We just figured that one out, right? So we literally know that the work, we can substitute this magnitude, is just mgd. So the work is the 75 kilograms times 9.80 meters per second squared, and this person rises up 2.5 meters. You put all that together, everything's an SI, you find out the work this person did is 1,837.5 joules. No vectors, no directions, literally just figuring out a scalar. 1,837.5 joules. That's the answer. That's how much work that this person expended. Okay. Let's do another problem. OpenStack 7.6. What's that say? How much work is done by a boy pulling his sister 30.0 meters in a wagon as shown? Assume no friction X on the wagon. All right, so this came with a picture. So similar to the sled I drew. So I have a flat ground. Now I got a wagon. And there's a girl in this wagon and being pulled by her brother. Or there's the boy. And art's not my strong point. All right, so there you go. The boy is pulling up at 50 newtons. And the displacement that she's going to pull this wagon is going to be 30 meters. Okay, and the angle here is 30 degrees. All right, so again, this is a basic work problem. And so I'm going to erase it. get going here. So, what's work? Work is, again, the dot product of the force and the displacement. Work is the magnitude of the force times the magnitude of the displacement times the cosine of the angle, or cosine 30 degrees. Work, we find that the magnitude of the displacement is 50 newtons. The distance is 30 meters. And times the cosine of 30 degrees. We find out that the work is 1,300 joules. Okay? So really the only work that's important is that work that goes along in the direction with the displacement, or the force component in the direction of the displacement. Now, what's interesting is kind of given aside here. So imagine here for a moment, I have my cell phone, and I'm gonna basically lift my cell phone a certain distance. And again, I just did this calculation that if I lift my cell phone up some amount d, that the work is going to be mgd. Why? Because the force that I'm applying against gravity and the displacement are at 0 degrees to each other. They are aligned. What if I do this instead now? I have my cell phone at this height, but now I'm going to go over by an amount d. Have I done any work now? Well, let's see here. The force that I'm expending to hold the cell phone up is an upward force. I mean, if I drop the cell phone, it's going to go straight down. So the fact of the matter is, it's being held up by a certain force. However, the displacement is 90 degrees to the force. The force is straight up. The displacement I'm doing now is 90-degree angle to it. So what would the work then? What would the work be now? Well, in this particular situation, my work would be what? It would be, I'm holding up the phone. So the work would be whatever the force is to hold up the phone. Again, I could do the analysis and realize that's equal and opposite to mg. The displacement, sure, there's a displacement, but it's the cosine. The displacement and the force, displacement vector and force vector are now 90 degrees. They're 90 degrees to each other. Cosine of 90 is 0. That means I've done no work. Now you try to tell that to a piano mover. These guys are like, get a heavy piano, and you say, hey, can you walk over there with this piano? And they're walking across, holding the piano at a constant height. Well, effectively, yeah, they're stressing and straining, and they're having a hard time. However, in a physics definition of things, they're doing no work because the displacement and the force are perpendicular to one another. Okay, so again, you don't want to. This is different than the vernacular. When you say work, it has nothing to do with things like I'm going to work or I'm working out. Anything like that. It has nothing to do with that. Work is a true, there's a true definition in physics for work. Okay? So again, keep that in mind. Don't let the vernacular get in the way. I mean, truly, if you are lifting a heavy item, you're going straight across, and your displacement is 90 degrees to the force, you are doing no work in the physics sense. All right, now, let's get a little bit more involved. OpenStack 7.5. Okay. It says calculate the work done by an 85 kilogram man. Who pushes a crate .00 meters up along a ramp. That makes an angle of 20 degrees. With the horizontal. He exerts a force of 500 newtons. On the crate parallel to the ramp. And moves at a constant speed. Be certain to include the work he does on the crate and on his body to get up the ramp. Okay, so OpenStack 7.5. Calculate the work done by an 85.0 kilogram man who pushes a crate 4.00 meters up along a ramp and makes an angle of 20 degrees to the horizontal. He exerts a force of 500 newtons on the crate parallel to the ramp and moves at a constant speed. Be certain to include the work he does on the crate and on his body to get up the ramp. Okay, so got all that. So let's draw this into a picture now. A bunch of words. Let's make a picture. So OpenStack 7.5. Let's do the problem. All right, so we have a ramp or an incline. Okay, right angle. We know what theta is. We're told that theta is 20 degrees. Now we have this crate, and we actually don't know what the mass of the crate is yet. So it has some sort of a mass. I could call it, I'll call it capital M, I guess. All right, whatever it happens to be. And of course, you'd want to use the tilted coordinate system in this particular case. So you'd want to have your positive X going along the ramp and your Y, positive Y, normal to the ramp. All right, and there, of course, there would be a normal force right here, and you'd have, oh, let's call this little m, I guess, and you'd have little mg going straight down again, just like last time, and you'd have coordinates here. This would be little mg, and this is also theta. This would be little mg sine of theta, and this would be mg cosine theta. And understand, we don't know the mass of the ramp, or sorry, of the crate. We do know the mass of the man. I'll call that capital one, 85 kilograms. Mass of man. We also know that there is a force that the man is pushing parallel to the ramp, an application force F. And that's 500 newtons. Okay, so that's parallel, it's totally in the x direction. All right, so now, and we're also told that that the crate is going to get moved a distance of d equals 4 meters. So it's going to be moved along the ramp at some d equal to 4 meters per second. Or maybe d is the entire, actually, I think d is actually the entire length of the ramp. So, but it's going to be displaced by an amount d. So the ramp is d, and that's 4.00 meters. Now I want to try to find out how much work the man does. So let's talk about the crate first. Let's work on the crate. And I'm actually going to do the crate problem 2 different ways. All right, and so your natural instinct might be to say, well, you know, the force and the displacement are along this x-axis. So wouldn't it just be the work done on the crate is the force and the displacement are absolutely parallel. So FD and the cosine of the angle between them is 0. That's totally legitimate. You can think about the force going along your new x-axis. The force is horizontal. There's the mass, and it's moving the mass up for a distance of 4 meters. So I could do this really quickly. The work done on the crate will then be 500 newtons. Go a little further to the left here. So work done on the crate will be 500 newtons. 500 newtons times 4.00 meters times that cosine of 0, which is 1. So I find out that the work done on the crate by the man is 2,000 joules. Okay, that's an important piece of information. So I got it that way. I know that the man can, basically does work to move the crate up the incline, and does work to a tune of 2,000 joules. Now I'm going to do this same problem, but in a more interesting way. So let's remember how I did this. So again, I did it in a simple way, and I realized I'm going to kind of put this in the storage here, that I did work. The man does work on the crate. We just did a simple calculation of the displacement along the x-axis, along the incline, and we realized that we can calculate the work done on the crate as 2,000 joules. Okay, so we'll keep that in storage. But I want to look at a different way. We can look at it as, we know that the system has no friction. Okay, and then, so the work the man does, so the work the man does is against gravity. And we also know that he pushes it up at a constant velocity. So he pushes the crate up at a constant velocity. So what we can say here is we can apply Newton's second law. Again, I'm going to say this an alternative way. I'm going to apply Newton's second law. Sum of all forces in the x direction is going to be the application force that the man is applying, that the man is pushing the crate, and then minus what? The component of weight going in the x direction, which is going to be negative. So minus mg sine of theta. And we said there's no acceleration. The man is applying constant, he's pushing it up at constant velocity. That means there's no acceleration. The right-hand side of Newton's second law is going to be 0. So what that means is I can actually figure out the mass of the crate through this relationship. I can say, okay, well, mg sine of theta is equal to F, the application force. And I know g sine theta, so I can solve for the mass of the crate this time. F divided by g sine of theta. So I get the mass of the crate. Is, again, the applied force of 500 newtons divided by 9.80 meters per second squared, and a sine of 20. Yeah, still love it. So I will find that the mass, I'm just going to write it up here, of the crate when I do this, the mass of the crate is 149.2 kilograms. So I can apply Newton's second law along the x direction, understanding that the crate's being pushed up at a constant velocity, and I can get that the actual, the mass of the crate is 149.2 kilograms. So I'm going to store that as well. That's an important piece of information. Now, what am I going to do now with that? Well, again, I can look at this situation as the crate being lifted up by gravity, or lifted up against gravity. So I can look at this and say, well, I know that in the same token that at the end of the day, the crate's going to start down here and it's going to be lifted up against gravity. So I can kind of redraw my triangle and say, yeah, I know that this height is h. I know this angle theta, and I know this d, 4 meters. All right, and so what I can do is find h, and that's simple trigonometry, opposite over hypotenuse, right? So the sine of theta is just h divided by d, opposite over hypotenuse, or h is d sine of theta. And so, well, what is that? Well, it's h is 4.00 meters times the sine of 20 degrees. And I can see that h, when I do this, is going to be 1.37 meters. So I can look at the work being done by the application of this application force F pushing it up the ramp. I can also think of this as work being done against gravity. There's no friction in the problem. And essentially what's going to end up happening is the crate is initially at the ground level, and it's going to end up being at a height h up. We think of this as h. So if I were to try to imagine this crate being lifted up by an amount h, I can do this problem a different way. I can say, well, the work done by the crate, I can think of this as basically F, the magnitude of the force, that I would actually be lifting it, times, what's the different F? I'm working against gravity, mg, again, whatever the application force going up is mg, times h, the height, times the cosine of the angle between the application force. If I'm looking at it vertically, and again, the application force, you can think of it this way, and h are aligned, so that's a cosine of 0 degrees. I can think of this as mgh, or the work by the crate. I calculated the mass, 149.2 kilograms, times 9.8 meters per second squared, times h, 1.37 meters, and cosine 0. If I multiply all this together, lo and behold, I find out that the work done on a crate is again 2,000 joules. I can look at it two ways. I can think of this as work being done by pushing the crate up the ramp, or I can likewise think of this as work being done against gravity to essentially lift this m times g a height h. Both ways, I find out that no matter how I calculate it, the amount of work done by the man on the crate is indeed 2,000 joules. I have two different alternative approaches to solve this problem. And in fact, that's the work on the crate. And I can use the same philosophy to talk about the work done by the man on himself. Okay, so the man on this body. I mean, again, we can kind of look at that as, well, the man is effectively lifting himself up as well. So the work done by his body will be capital Mg, being capital M being his body mass. Again, H, the same height, time, and again, these are aligned, so cosine is 0 degrees. And the work done by on his own body will be 85 kilograms times 9.80 meters per second squared times 1.37 meters. And I find out that the work done the man does on his own body will be 1,141 joules. Okay, so the man did 1,141 joules to lift his own body up the ramp. And he's also done 2,000 joules to get the crate up the ramp. And this the beauty about energies is they just add like scalars. I want to find the total work that the man did. Well, that's easy. Energies just add as scalars. No vector, nothing. I mean, you just add up the numbers. That's the beauty about energy. The total work, we'll say work total, is the work that he did on to lift his own body up the ramp, plus the work that he did to lift the crate up the ramp. It just literally just add. So the total work done by the man will be the 1,141 joules plus the 2,000 joules. And that's just equal to 3,141 joules. And that's what makes energy so nice, is that literally when you figure out the energies, you literally just add them up. Okay? That's OpenStack 7.5. Now we have a new concept now. So we have this concept of work. That's one form of energy. Okay? Now, let's talk about, so as you know, we have what's called an energy of motion. If something is moving, it has an energy as well. All right, and so let's try to figure that one out. So again, if I have a network, that's going to equal a net force times a displacement. So again, if you have a bunch of forces on an object and you get a net force, you get a resultant force, you multiply it by the displacement. Again, I'm just kind of doing things, you know, I'm kind of assuming things are aligned. I don't worry about cosines and stuff. Then I get a net work. Okay, well, let's look at Newton's second law. That says that the net force is equal to the mass times the acceleration of the body. So I have this body that I'm moving, and it accelerates. So the net force on this body is ma. I can combine the two. I can say, well, the net work is MAD. MA, and then I still have the displacement. All right, well, what do I know? I have a body of mass M. Is accelerating at A. It must have had an initial velocity and a final velocity. I'm going to get a body, it's going to have initial velocity. You're telling me there's a body that's accelerating. It means it's going to have an initial velocity during this acceleration phase and a final velocity, right? Going back to chapter 2. Well, let's go back to our kinematic equations. Well, remember we have a kinematic equation. We have v squared equals v naught squared plus 2a x minus x naught. Remember that from our kinematic equations? Well, in this problem, let d equal x minus x naught. So our equation then becomes v squared equals v naught squared plus 2ad. Let's solve for AD. AD is going to be v naught, so v squared over 2 minus v naught squared over 2. And let's do this. Let's take this formula and let's plug it in here. Okay, we got this AD that we got from our kinematic equations. Let's plug it into this formula and see what happens. All right, so doing so, we get the network is m times what? V squared over 2 minus v naught squared over 2. Or the work net is 1/2 mv squared minus 1/2 mv naught squared. So we know that the work is an energy. But this other quantity, which is 1/2 times the mass times the speed squared, that's an energy too. It's got to be, because energy must equal energy minus energy. You have to add like things, right? And so this has got to have units of energy. It's a special kind of energy. So what we've just gotten to deriving is actually two very important statements. First of all, we just got done deriving a new form of energy, an energy of motion. We'll call it the kinetic energy. And in fact, we also realized another thing, that work being done is equal to a change in this kinetic energy. We refer to that as the work energy theorem. Okay, so we just got done deriving two very important things. Two things in once. And that is, we have a new kind of energy. Kinetic energy. So if a body has a mass m and is going at a speed v, its kinetic energy is 1/2 mv squared. We also know what we call the work energy theorem. And that is simply that the net work is the change in the kinetic energy. So two very important results. We have derived a new form of energy. If an object has a mass m and it's in motion with a velocity v or speed v, it has kinetic energy, 1/2 mv squared. The other thing is, if work is being done on an object, it changes the kinetic energy. Likewise, if you notice that an object is changing kinetic energy, that must mean that work is being done on it. So again, it goes both ways. So we have a new form of energy, again, kinetic energy. Let me do some problems. Okay. So here we go. Work energy theorem, kinetic energy. A new form of energy. Now we have two forms of energy. We have work and we have kinetic energy. We realize the two go together. OpenStack 7.9. Compare the kinetic energy. This is a very interesting problem. Of a 20,000 kilogram truck. Moving at 110 kilometers per hour. With that of an 80 kilogram astronaut. In orbit, moving at 27,500 kilometers per hour. All right. So big truck moving at a not so fast speed compared to the little astronaut moving at an extremely high speed. So who has more kinetic energy? Okay, so you got that. So again, this is simple calculation, but it's going to have an important result here. So I'm going to erase this now. So we need to figure out, so first of all, let's do the truck first. So the mass of the truck, I'll say capital T for truck, is 20,000 kilograms. The speed of the truck, okay, we're told it's 110 kilometers per hour, but that's not going to do us any good. We need to convert that, right? So we know there's 1,000 meters and a kilometer. Kilometers cancel. And an hour has 3,600 seconds. We find out we have 30.56 meters per second. Okay, velocity of the truck or speed of the truck. All right, we need to find out, okay, if we have the mass of the astronaut. I'll do A for astronaut. We find out that's 80 kilograms. All right, so truck, astronaut. And of course, we have the same problem. The velocity, speed of the astronaut, again, we get this big number, 27,500 kilometers per hour. And I got to do the same thing again, 1,000 meters in a kilometer, and an hour has 3,600 seconds. I find out that the speed of the astronaut, when I do all of this, is going to be 7639 meters per second. All right, so I have all the information that I need. Now, unfortunately, I'm going to ask you to remember this because we're going to now do the calculation. So let's get the kinetic energy of the truck. So remember these numbers. Kinetic energy of the truck is 1/2 mass of the truck, speed of the truck squared. Okay, kinetic energy of the truck is 1/2 mass of the truck, big, 20,000 kilograms, going at 30.56 meters per second. Squared. The kinetic energy of the truck. You do that, you find out that it's 9.34 times 10 to the 6 joules. Okay? How about the astronaut, little astronaut? Kinetic energy of the astronaut is 1/2 mass of the astronaut, speed of the astronaut squared. And it's 1/2, the astronaut's 80 kilograms, and he or she is going at 7639 meters per second, quantity squared. And we find out the kinetic energy of the astronaut is going to be 2.33 times 10 to the 9th joules. 2.33 billion joules. Compared with the truck, it's 9.34 million joules. So even though the astronaut is small, very small compared with the truck, it's going around in orbit so fast that it has an incredible kinetic energy, 1,000 times that of the truck. Now, this kind of reminds me of a story. So these astronauts are sitting in this is a true story. These astronauts are sitting in the International Space Station, and they're going about their work, and all of a sudden they hear this huge bang against the space station. They're like, "What in the world hit us?" And they're looking around. They can't figure out what in the world caused that giant wallop. Finally, they figured it out. It was a paint chip in orbit. A little paint chip going at some crazy velocity, like 27,500 kilometers per hour, and it hit the space station with a wallop. I mean, this little paint chip. And so that's one of the problems that we have right now with low Earth gravity is that, like everything else we do as humans, we just create a bunch of junk. So we end up having junk floating around in orbit, and of course, this is junk that's floating around at a very, very high velocity with a very high kinetic energy that can cause damage to stuff like satellites. So it turns out that you're going to have to, any little tiny thing, even a paint chip that you might lose in orbit, you need to track that, you need to record that, you need to know where that is, because even if it's just a paint chip, it can cause a lot of damage. All right, so again, we have an issue with junk in space now, polluting space. All right, so all right, we have let's do 7.12. of OpenStax. Okay, so 7.0 of OpenStax says, A, calculate the force needed to bring a 900 kilogram car to rest. From a speed of 90 kilometers per hour. In a distance of 120 meters. And basically a fairly typical distance for a non-panic stop. All right. And then B, suppose instead the car hits a concrete abutment. At full speed. And is brought to a stop in 2.00 meters. All right, so we're going to compare these two forces. All right, so calculate the force needed to bring a 900 kilogram car to rest from a speed of 90.0 kilometers per hour and a distance of 120 meters, a fairly typical distance for a non-panic stop. B, suppose instead the car hits a concrete abutment at full speed and is brought to a stop in only 2.00 meters. Okay, so again, this is the kind of force you're going to see here is going to be more or less instant death. You're not going to be able to survive that. All right, so we're going to erase this board here and then do the problem. All right, so that's why you want to drive carefully and don't drink and drive. So, all right, so part A, the mass is 900 kilograms. Mass of this big car. The initial speed, initial velocity or initial speed is going to be V naught. We're told it's 90 kilometers per hour. And again, that doesn't do us any good. We're going to have to convert that, of course, right? So got to get that in meters per second. Got to get it in meters and seconds, not kilometers an hour. So again, there's 1,000 meters in a kilometer. Kilometers cancel. And I got to get rid of hours. So put hours on top. Hour per 3,600 seconds in an hour. I find out that the initial speed of the car is 25 meters per second. The final speed is coming to rest is going to be 0. The displacement of the car as it's decelerating is 120 meters. And so the question is, what's the force? So what do we do? Well, we can use the work energy theorem. Okay, and so what do we do? Well, we remember that the work is the change in kinetic energy. All right, so the work is going to be like a net force times the distance, right? So there's a force that's being applied to stop the car, a braking force, over a distance of 120 meters. It's going to be work to make that happen. And that's going to equal 1/2 m v final squared minus 1/2 m v initial squared, right? We know that v final is 0, right? Because the final velocity is 0. It's coming to a rest. And so what we can do is we can solve, divide both sides by d, and we get that the net force, again, it's negative because it's decelerating. That makes sense. So it's going to be negative mv naught squared divided by 2d. It's negative because it is a decelerating force. It's stopping the car. All right, so we have negative, the mass of the car is 900 kilograms. The initial speed is 25 meters per second. Don't forget to square it. Divided by 2, divided by 120 meters. And I find out that the net force when I do this, I'm going to right over here, I guess. Let's see if I have room. Yeah. The net force we'll find is going to be negative 2474 newtons. In a typical non-panic stop. And I have the initial speed, final speed is 0, coming to rest. It's going to do it in 120 meters. And so work energy theorem, the net work, I guess I should really write it like this. Net work is delta kinetic energy. That's force net times the distance it took to stop. 1/2 mv final squared minus 1/2 mv initial squared. V final is 0, so solve for F net. Now, part 2 of this problem is really just like, part B is really just like part A. The difference is going to be the following. I do every single thing except this. Instead of having 120 meters, I unfortunately only have 2 meters. My denominator becomes much, much smaller, which means my fraction becomes much, much larger. It becomes crazy large. It becomes negative 1.48 times 10 to the 5th newtons. So this person is not going to survive this crash. There's no way. Those kind of forces on the body, that is too much trauma. Okay, so that's why, you drive responsibly, you don't drink and drive. I mean, that's because I have known people I know a guy who lost his son at a former company I worked because his son, I don't know why, fell asleep at the wheel, hitting a button on the freeway. So yeah, son didn't survive. So as an example. All right, now I'm going to go to the next topic now. So we're going to talk about another form of energy. So kind of go back to lifting an object up from a let's say a table or the ground. So let's recall, let me ask a question. What is the work done in lifting an object? of mass m through a height h. All right, so what would that be? Well, again, we're going to kind of assume, that we're lifting at a constant velocity. So assume constant velocity. Lifting. So what does that mean? Well, again, that would mean that the sum of all forces in the y direction is you're going to lift it at some sort of a application force F. The only other force that's on the body is its own weight. And again, if we're doing a constant velocity, that means that there's no acceleration. That means whatever the magnitude of this lifting force, it's going to equal mg. And I'm lifting it an amount h. So the work that we're going to do is the F dot h, or the work is the magnitude of F times the magnitude of h. And again, h is a displacement, force is displacement. They are aligned. So the cosine of 0 degrees. And I know what the magnitude of F is. It's mg. So I find out that this work is mgh. Now it comes to find out that's going to be a very important concept. We'll actually refer to this as a gravitational potential energy. Okay, so we'll find out that we can think of this combination as a gravitational potential energy. So typically we refer to this as a PE, potential energy, and that's mgh. Now let's take a deeper look at this concept of potential energy. Okay, so again, let's remember, this formula for a moment. Let's look at it in a more deep way. All right, so there's two types of forces in the universe, right? Two types of forces. You can divide it into categories. Conservative forces and non-conservative. Now, this has nothing to do with politics, okay? So again, this is just this is a physics term, conservative forces. All right, so first of all, what is a conservative force? This is what's really important here. So let's take a look particularly at what is a conservative force. All right, conservative force is one like the gravitational force, as an example. For which work done by or against it depends only on the starting and ending points. Of the motion. And not the path taken. And then we can define a potential energy for any conservative force. The force must be conservative to have a potential energy. Okay, a conservative force is one, like the gravitational force, for which work done by or against it depends only on the starting and ending points of the motion and not the path taken. We can define a potential energy for any conservative force. So to have a potential energy, the force must be conservative. So let's give an example of what I mean by endpoints, not the path taken. So let's just, for instance, I just got done telling you that if I take a mass, like my cell phone, and I lift it up by an amount h, that I just got done saying that the potential energy associated with that is mgh. Now, it doesn't matter if I lifted it along this path straight up, or what if I did this? What if I just did some little ziggy zag, and yet I got into the exact same final position? The thing is, even if I started from what we would call, say, the zero potential at the bottom here, and I go straight to the top, and yes, mgh, or I start from the bottom again, and I do this zigzag stuff, I do all this, this crazy motion, and I get exactly where an exact same endpoint, it doesn't matter. Because it's the gravitational force, because it does not matter what path I took. As long as the endpoints are the same, the potential energy calculation will be the same. It does not matter if I took the mass and went straight up, or I took the mass in some loop-de-loop pattern and got the same final position. The fact of the matter is the potential energy and the beginning and the end only depends on the endpoints, not the path taken. On the other hand, an example of a good non-conservative force would be friction. If I decide to take my phone, I rub it one direction and give off friction, well, I'm not going to get the energy back by rubbing it in the reverse direction. All I'm going to do is just rub the phone and expend more frictional energy. It's kind of like, you remember Ferris Bueller's Day Off, he put a bunch of miles in his dad's car and he's putting it in reverse to try to get the miles back off, right? Well, a non-conservative force doesn't behave that way. You can't just go the other way and get your energy back. In fact, if I decide I'm going to go straight from one place to another and rub against the surface and give off friction, well, if it's a straight path, it's going to be less friction than if it's a curvy path, right? Because I'll just have more surface that I'm rubbing against. So again, the path taken for friction is very important. You will, if you take a longer path and you're rubbing it, against a surface, you're going to expend more energy than if you took a straight path. All right, and so again, the path matters. So there's a lot of there's a lot of conservative forces, and you cannot define a potential energy for friction. It is not possible. Okay, so let me kind of write down. So gravity is an example of a conservative force. Now, a non-conservative force would be an example, as I said, would be friction. So let me kind of write down what I just got done saying. An example of a non-conservative force is friction. Friction, so the force of friction does indeed depend on the path taken. You cannot you cannot express a potential energy for friction or any other non-conservative force. Only conservative forces have potential energy. Okay, what's another conservative force? Well, we're going to find out, and we'll study this force more when we talk about oscillations, which is a fancy word for saying vibration. But another form of a conservative force is the spring force. We call it Hooke's law. So we have a mass on a spring, for instance. You know, we realized that, for instance, we had a lab on this recently. But if you imagine, for instance, you have a mass, and we're going to say that there is no friction between the surface and the block. And in an equilibrium position, there is a spring to this between the mass and the ball, and this is a wall. Okay, springs always are defined by a spring constant K, just like we said in the lab. There's always a parameter called K, and this is the mass. So K is a spring constant. It is a characteristic of all springs. Now, there's a contemporary of Sir Isaac Newton. His name is Robert Hooke. So we have what is called Hooke's law. Now, it turns out that Isaac Newton, just like Gottfried Leibniz, Isaac Newton absolutely despised Robert Hooke as well. That's one of the guys that Isaac Newton hated. But we have Hooke's law. Hooke is actually a very, very good scientist. I'm not sure why Newton felt that way, but Hooke's law basically says that if I compress or stretch this mass, let's just say, for instance, here is the equilibrium position of this mass. Okay, so let's just say that this is where it used to be, but I'm gonna now compress it. I'm gonna move it in from this equilibrium position, and I'm gonna push the mass in. And now the mass is located here, and now I'm compressing the spring. Okay, I have now displaced it by an amount x. X is now my displacement. So displacement of the mass on a spring. Okay, we come to find out that there will be a force that will oppose this action, and it's given by Hooke's law. Hooke's law says, no, there's going to be a force of the spring that's going to push back, and it's going to be equal to negative kx. Negative the spring constant times the displacement. This is the force, the resistive force the spring applies. And again, it works both ways. If you're trying to compress it, Hooke's law will push against you. If you try to stretch it, Hooke's law is going to try to pull the mass in. Again, it's a resistive force. From the spring. Now, what's interesting here is that now this negative sign, the only thing that negative sign means is that the force is going against the displacement. So if you're compressing it, the force is going to try to fight against that compression. If you're stretching the spring, the force is going to try to pull it back in and fight against that as well. And again, the K is a constant, and I'll show you how you can figure it out. I mean, we talked about this in the lab, but essentially the more you either compress or stretch, the more the displacement is, the greater the resistive force. And in fact, this is a linear equation. Now, the question is, well, how do you find, for instance, the spring constant? Again, this is a good problem for, I take a spring. You hand me a spring and you say, find the spring constant of this spring. How would I do it? Well, what I would do is I would hang the spring upside down from the ceiling. And I'd figure out where, there's some sort of x naught that the spring naturally sits at in its equilibrium position. But now I'm going to go and hang a known mass. Let's say I know a certain mass and I'm going to hang it. So we're now going to hang a known mass, M, on the spring. What's going to happen is it's going to stretch the spring out, right? So let's just say, and this is the second case here, I'm going to take the same spring, but now I'm going to hang a known mass on it. And I realize that now there's been a displacement y. We'll say this is y naught. Okay, so this is the initial equilibrium position. Now the spring has been displaced by an amount y. Okay, so if you're stretching the spring, what's displacing the spring? What's displacing it? Gravity is, right? So there's a weight that's causing this displacement. And of course, if you're going to displace the spring, then it's going to be met by what? Resistive Hooke's law force, Ky. And it's going to resist, so it's going to be that direction, that displacement y, the force constant k, and it's going to resist. And if this spring, and if this mass sits motionless, that means there's not going to be any acceleration. So I can take Newton's second law, sum of all forces in a y direction. Ky is the Hooke's law force going up minus mg, and there's no acceleration. So what I can actually do is say, well, Ky is equal to mg. And I can now say, well, I can now figure out my force constant, K, is mg divided by y. As I said, the mass is known. I know g, I'm on the Earth, 9.8 meters per second squared, and y, I can measure that. So now I can do all that. I now can figure out from here on out what this spring constant is. And its units are newtons, m times g, per meter. That is, so when you have a spring constant, the units of that are newtons per meter in SI. Now, I'm going to figure out in general, what how to figure out, I'm going to figure out the work in general. How do I figure out the work? Well, and that's just, a side about the spring. So let's say, for instance, I know that if I have a constant, if I have, say, some constant force going at some sort of a displacement, well, what's the work? Let's say, here's my displacement, 0 to x. What's the work going to be? Well, we know the work is the force times displacement, right? That is the area underneath the force. If we take the force displacement curve, that's the area underneath that curve. F times x. If I have some sort of a force F and I'm going at a certain distance x, the area under the curve is the work. So work equals the area under the force displacement, or area under the curve, and a force displacement graph. Well, that's easy. The area of a rectangle is easy, right? Length times width. What happens, though, if I have a more general function? Say, for instance, it's not some pretty thing that looks like this. Let's say it's something that's more complicated. Let's say, for instance, that my function really looks something like this. Here I have the force, and I have displacement, force displacement curve, or force displacement diagram. But now the curve looks something more general. Something like that. And I want to try to figure out, well, I want to know what the area under that curve is. Let's say, I go from x0 to x1. What's the area? How do I figure that out? Again, it's still going to be the work is still the area under the curve on a force displacement graph. Well, what do I do? Well, I can approximate this by little rectangles. So I'll try to make little rectangles, maybe the same width, delta x, the best I can. And I want to try to add the area under the curve because I know how to calculate the area of a rectangle. And sometimes I do a good job, and sometimes I don't. Right? And so we can imagine that each of these widths of rectangles is delta x. And there is some sort, we can say it's a delta x sub I. Okay, so again, I is a counting number. 1, 2, 3, 4, 5, 6. I is a counting number. I'm counting out the rectangles, and I can actually figure out that as where the rectangle touches the curve, we can call that f sub I. And we can say, okay, well, hey, we can figure out the curve by saying that the work is the summation over I as I'm going along of f sub I times delta x sub I. I just add the areas of all these rectangles, right? But the problem is I'm not doing a very good job over here, at least. I'm missing parts of the function. You see these little error spaces? Well, that means my answer is going to have error, E-R-R-O-R, in it. How do I do a better job? Well, I consider, so we can do a better job. So again, this particular graph has error. So this calculation has air? Well, we can consider skinnier rectangles and more of them. But we'll still have air. For us to really do it right, we'd have to take the limit as delta x approaches 0. We'd have to take an infinitesimally thin rectangle and an infinite number of them. And what this tells you is you need to employ integral calculus. In the most general sense, the work in general requires integral calculus. It requires the integral from, let's say, x0. Let me write this better. So we need to take the limit, we need to approach calculus. So the work in general will be the integral from, let's say, where I'm going, x0 to x1, my endpoints, of, in the most general sense, f dot dx. It is the area of the curve that requires integral calculus in the most general sense. So if I really want to find the work in a general function, I cannot avoid using integral calculus. But let's go back to the mass on a spring, Hooke's law. What does Hooke's law look like? Again, this was integral calculus, by the way. This is calculus 2. So calculus 1 is the slopes, or we call it the derivatives. Calculus 2 is the integral calculus. All right, so let's go back to Hooke's law. What did that look like? Well, the force is kx. I'm gonna neglect the minus sign. What does that look like on a force displacement curve? Let's see. Kx, that's linear, right? So here's your force, and here's x, and it's a nice line. So if I want to go and say, I want to go out to some sort of a displacement x, and I know that at this special value of x, this function is going to be what? It's going to equal kx. So at a particular value x, the function has a height kx. Well, this is a triangle, right? It's a right triangle. How do we not? So I don't need integral calculus to figure out the area of a triangle, right? Area of a triangle. So area of a triangle is base times height, 1/2 base times height. The area of a triangle that's equal to 1/2 base times height. Okay, back in your previous math. So that means that the work is the area of this curve, 1/2 base times height, huh? Well, we see 1/2. The base is x, and the height is kx. Putting it together, I find that the work for a mass on a spring is 1/2 kx squared. Again, this is a mass on a spring. So if you compress, it takes this much work for, if you have a spring with a spring constant k, you compress it by an amount x, or you stretch it by an amount x. It takes this much work to do that, 1/2 kx squared. Either compress it in by an amount x, or to stretch it out by an amount x. 1/2 kx squared. Now, it turns out that the Hooke's law force is a conservative force. I can undo, if I pull it out, I can undo the force. I can get back in the original configuration. It's path independent. And in fact, it only depends, the configuration only depends on the endpoints. So it turns out the Hooke's law force is conservative. that means that there's a potential energy. All right, so Hooke's law of force is a conservative force, just like gravity. So that means the potential, so it has a potential energy. It has a corresponding potential energy. And it is given by potential energy. PE is 1/2 kx squared. We can think potential energy as energy storage. Like energy stored in the compressed spring. Now, if you look at your garage door, for instance, there are springs in the garage door under tremendous compression. And you've had one, I've had one break before, and it makes a huge bang sound. I mean, it can actually really, really damage you. In fact, if you do not know what you're doing, you better not be trying to fix springs like that in your garage door. You will really, really hurt yourself, because these are under tremendous compression. You can kill yourself, basically. All right, and so essentially, there's a tremendous amount of energy that's stored in a coiled up or compressed spring. In the same manner, you can think of, well, I have this this cell phone. Now I'm free to always define my zero potential energy however I wish. The only thing that matters about potential energy is different. So if I imagine the cell phone sitting up here, it is like, if I let it go, it's going to fall, and there's stored potential energy in this cell phone. And the potential energy is energy of configuration. It's an energy because it has a certain position. So again, potential energy we can think of as an energy, just like we thought of kinetic energy as an energy of motion. The potential energy is an energy of configuration. Okay, so potential energy is an energy of configuration. Okay, and so very important concept. Now, all right, let's see here. Now we go back to energy conservation again. And one of the problems with energy is it's squirrely. Energy gets lost really easily, and that's why I talk about my Chuck E. Cheese game tokens example. Energy, you lose energy a lot. The problem with energy is it dissipates really easily. If you think about even with, like, say hitting a cue ball, oftentimes in pool you try to think of a good example of something that conserves energy as a cue ball, a stick hitting a billiard ball. The fact is, if I were to play a sound bite for you of a pool ball getting hit, you would recognize it immediately. So the very fact that you hear it means there's energy, sound energy being given off. Energy is being given off all the time, and you don't get it back. All right, so the energy you get back are energy dealing with conservative forces. So let's talk about what's called it. So again, it's difficult to apply a conservation of energy. Yes, indeed, energy is conserved. but most of the time it's not useful. All right, so it's really, it's really not useful, to apply a conservation of energy, because oftentimes energy is leaky. It leaks. All right, so let's think about particularly the conservation of mechanical energy. Okay, so if we look at the work energy theorem again, you can always write down that the net work is the change in the kinetic energy. Or you can write that the net work is 1/2 mv final squared minus 1/2 mv initial squared. You can always write that down. Now, what if your work net is entirely conservative? So all the forces in this problem are conservative. So we'll say the entire net work is due to conservative forces. Hence the C that we see here. Well, what's the case if that's true? Then that means that when you perform work, it's at the expense of potential energy. So for instance, if you have something that has potential energy and you drop it, or let's say my cell phone again, so this thing has potential energy. What's going to happen is right now it has no kinetic energy whatsoever. But now I'm going to drop, if I drop it, I will gain, it'll go faster and faster, I'll gain kinetic energy, but I'll lose potential energy. So potential energy, work is always done at the loss or at the expense of potential energy. So effectively, conservative work is always done at the expense of potential energy. I have to lose potential energy to gain kinetic energy or to do work. All right, so what does that mean? Well, that means that what I can do is I can basically substitute right here. So for the work energy theorem, instead of saying work net, what I can do is I can put in the negative potential energy here. So work net is really the same as negative delta potential energy is delta kinetic energy, right? So all I've done is originally I wrote down that the net work was the exchange of kinetic energy. But now I realize that for conservative forces, only conservative forces, then I can actually replace the net work with negative delta potential energy, again, for conservative work. What does that mean? Well, I'll add both sides of potential energy. I'll say that I can actually write delta kinetic energy plus delta potential energy equals 0. Okay, well, what's that mean? Well, what's delta kinetic energy? Well, that's kinetic energy final minus kinetic energy initial. Delta potential energy. Potential energy final minus potential energy initial. What I can do is I can throw all the initial, and that's equal to 0. I can throw all the stuff that I've labeled as initial on the other side. But what do I get? I have kinetic energy final plus potential energy final equals kinetic energy initial plus potential energy initial. It means they're always equal to the same total mechanical energy. That means no matter what, if I lose kinetic energy, I'll gain potential energy, or vice versa. That this is they always have to equal a total mechanical energy. So this right here is total mechanical energy. That means if I add up the potential energy and the kinetic energy, if I have only conservative forces acting, then they will always add up to the same thing. So again, this is total mechanical energy. Kinetic energy, if only conservative forces are working, that kinetic energy plus potential energy at any time is going to add up to the same value. And hence I get a conservation. Only if we're talking about conservative work. Now, what happens if you have non-conservative work in there? Okay, so what happens if you mix in non-conservative forces? So now we'll consider non-conservative forces. So going back to basics, what do we know? Well, we know that the net work is going to be contributed by what? Conservative work plus non-conservative work. There's going to be work done, due to conservative forces and work due to non-conservative forces. All right, and so that work net is still going to be the change in kinetic energy. Again, work net is always equal to the change in kinetic energy, but now we just don't have just conservative forces anymore. Now we have non-conservative forces mixed in. Well, remember, for conservative forces, I can always associate a potential energy. So conservative work is always done at the expense of potential energy. So I can substitute that in there. I can say, okay, well, negative delta potential energy plus non-conservative work is the change in kinetic energy. All right. Well, what does this mean? Well, what I then have is see, change potential energy. Well, I have a negative here, right? So that would then be potential energy final minus potential energy initial plus non-conservative work equals kinetic energy final minus kinetic energy initial. So what I can do is I can realize that, well, let's throw all the initials on this side. So let me plow this negative sign through. So negative potential energy final plus negative is a positive potential energy initial plus non-conservative work is kinetic energy final minus kinetic energy initial. What am I going to do? I'm going to put all the initial stuff on one side and the final stuff on the other side. So I'm going to move this kinetic energy initial to the left. I'm going to move the potential energy final to the right. And I'll find out that I have kinetic energy initial plus potential energy initial plus non-conservative work equals kinetic energy final plus potential energy final. If I didn't have any non-conservative work, then I literally would have a balance. But the fact that I lose energy, the fact that I'm going to come out if I add up the final kinetic energy and potential energy, it's going to be less than what the initial kinetic energy potential energy is because of this non-conservative work. The fact that I'm going to lose energy is because of this non-conservative work. So in general, this is what it looks like. So basically non-conservative work. So non-conservative work always adds or subtracts energy from the system. Okay, either energy. So in case of friction makes you lose energy. So it's always either going to add or subtract energy. So non-conservative work is a reason why you'll notice that certain things eventually die out. You're not going to have a pendulum clock that's going to go forever unless it's being helped along by some little extra boost. So things are eventually going to die out. You don't see things going forever because eventually non-conservative work will dissipate the energy away. Okay, so now again, as I said, there are many types of energy. And I've talked about various types of energy already. I've talked about potential energy, kinetic energy. I've talked about work. We also have other forms of energy. We have electrical energy. We have chemical energy. We have radiant energy, like light. Nuclear energy. And thermal energy, and we can go on and on. All different forms of energy. Okay, we can go on and study all of them. But again, we've studied a number of them here. So what I'm going to do is I'm just going to kind of work a few problems out, and let's kind of get ourselves situated here on conservation of energy. All right, so I'm going to look at Cutnell Johnson. So again, we're doing open sex. Now it's going to do Cutnell Johnson. 6.41. Okay, what's it say? A 47 gram golf ball. 47.0 gram golf ball is driven from a tee, or driven from the tee with an initial speed of 52.0 meters per second. And rises to a height of 24.6 meters. Okay. A, neglect air resistance. And determine the kinetic energy of the ball at the highest point. B. What is the speed when it is 8.0 meters below the highest point? Okay, so first of all, it's very important that we first of all realize that we can neglect air resistance. And why that's important is because that would be the friction in this problem. That would be where you would have some sort of losses. But given I can neglect air resistance, it means I can actually apply the conservation of mechanical energy. Okay, I'm going to erase this now. So that means that if since we can neglect air resistance, this problem will not have non-conservative work and we can employ conservation of mechanical energy. i.e., kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. Okay, we're going to define the ground as the zero of potential energy. You are free to define whatever you wish as the zero of potential energy. Again, the only thing that matters with potential energy is the change in potential energy. So I'll define the ground as the zero of potential energy. Okay, which means that when the golf ball is being hit off the tee, that potential energy is zero. That means that the entire energy of the system will be entirely kinetic energy. But the entire energy at some other later point in the trajectory will be a combination of the kinetic energy and potential energy at that point. However, we define as final. Well, in our first case, we're defining the final as the height of the trajectory. Okay, so simplifying things, I can then say that, again, kinetic energy initial, I just knocked out the initial potential energy term. So kinetic energy initial is equal to kinetic energy final plus potential energy final. Now, we're going to say that the ball is being hit off the tee at some V naught. So what's kinetic energy? It's always 1/2 mv squared, right? So 1/2 mv naught squared. Ball's getting hit off the tee. All right. And there's going to be some sort of final velocity when it's at its highest peak, 1/2 mv squared, and it's going to have a potential energy of mgh. So again, we know V naught. We're told V naught. we're told that V naught is equal to 52.0 meters per second. We're told that. We're also told the highest point. The highest point is going to be at 24.6 meters. And V is the speed of the golf ball at the highest point. That's your final. Now, something nice you can see here is that I actually can cancel out the masses. Masses are common everywhere. I can cancel them out. I can multiply through by 2. And interestingly enough, we get a, let's see here. Okay. What am I looking for now? Oh, it's a kinetic energy highest point. Never mind. Never mind what I just said. So, yes. Hang on one second here. I don't want to go this deep yet. So I do know this, but we're gonna keep them all in terms of. All right, we're gonna keep these in terms of the kinetic energy. So we can express the potential energy. The way this problem is worded, we want to find the energy. So never mind what I just said. So kinetic energy initial, and this is kinetic energy final. All right, so this is all stuff we do know, of course. So now we want to find the final kinetic energy. So we can solve for it. We can basically say that the final kinetic energy is the initial kinetic energy minus mgh. Okay, and we can say that, okay, well, that's going to be 1/2 m v naught squared minus mgh, or we can say the kinetic energy final. I can pull the m out, and I'm left with 1/2 v naught squared minus gh. Okay, and so I'll finish the problem up here. The kinetic energy final is the mass of the golf ball, 0.0470 kilograms, times brackets 1/2 the initial velocity, 52 meters per second squared, minus 9.8 meters per second squared, times the 24.6 meters. Yeah. Minus 9.80 meters per second squared times the 24.6 meters. All right, and so if I do all of that, I find, let me just write this out again. All right, again, make it a little prettier. Kinetic energy final, as we just got done saying, will be m times 1/2 v naught squared minus gh, and kinetic energy final will be the mass of the golf ball, 0.0470 kilograms, times brackets 1/2 52 meters per second squared minus 9.8 meters per second squared times 24.6 meters. I come to find out that the final kinetic energy, when I do all of this, keeping it all in SI units, the answer is going to be in joules. It'll be 52.2 joules. That'll be the kinetic energy of the golf ball as it's at the top of its trajectory. Okay? Now, we want to consider basically what is its velocity when it is 8 meters below the top of the trajectory. Okay, and so we're just going to pick a different final. So again, we're still applying the conservation of mechanical energy, kinetic energy initial. Part B. Plus potential energy initial is kinetic energy final. Plus potential energy final. They all, kinetic and potential energy always have to add up to the same value with conservation of mechanical energy. Okay, and so in that case, again, the initial potential energy, I'm defining the ground to be initial potential energy of 0. So what this means is that I know that this is 1/2 m v naught squared. And again, I'm looking for the velocity. This is going to be whatever the velocity is. If v is the velocity at that special point, and then this is going to be mg, and I'm going to call it h2. H2 will be 24.6 meters, the highest point, minus 8 meters. Remember, we're asking about 8 meters below the highest point, and we come to find out that's actually going to be 16.6 meters. And so in this particular case, we can actually cancel out the m's, like I said before, multiply through by g, and you actually find this formula that looks like something you got from the kinematic formulas. I can actually say I can solve for v squared. That's what I'm looking for. Multiply through by 2, I get v naught squared. Plus, actually, it's going to be minus, carrying this over to the left, 2gh2. And again, that ends up looking like you got out of the kinematic formulas now. So v is v naught squared minus 2gh2. Take the square root. And that's going to be v is going to be the 52 meters per second quantity squared minus 2 times 9.80 meters per second squared times 16.6 meters. Square root of all that. I come to find out that speed the projectile has when it's 8 meters below the pinnacle ends up being 48.8 meters per second. Again, I actually can do this problem for any point in the trajectory. You know, it doesn't matter how many meters below the max I go, I can go to any point in the trajectory and apply conservation of energy this very way. Okay? Let's see. Let me do a couple more problems here. We're almost done. This one's an interesting problem. Sometimes you're on a freeway and there's some big hills. You notice that if the hills are really bad, there's always a runaway truck ramp sometimes on the side. So if your big truck, semi truck loses its brakes, there's a runaway truck ramp that can allow it to stop safely. So let's look at this problem. It's going to be Cutnell Johnson 6.47. Okay, Cutnell Johnson 6.47 says a semi-trailer is coasting downhill along a mountain highway. when its brakes fail. The driver pulls onto a runaway truck ramp. That is inclined at an angle of 14.0 degrees. Above the horizontal. The semi-trailer coasts to a stop after traveling 154 meters. Along the ramp. What was the truck's initial speed? Okay, neglect air resistance and friction. So no losses. All right, so we said a semi-trailer is coasting downhill along a mountain highway. When its brakes fail, the driver pulls onto a runaway truck ramp that is inclined at an angle of 14.0 degrees above the horizontal. The semi-trailer coasts to a stop after traveling 154 meters along the ramp. What was the truck's initial speed? Neglect air resistance and friction. So that last sentence is very important because it says that I'm not going to have any losses in the energy losses in this problem. I'm not going to have any non-conservative work, which means that I can actually apply the conservation of mechanical energy. Okay. So again, let's work this out. Erase the board here. So that's got to be a scary experience, losing your brakes and having to go and stop at one of these runaway truck ramps. All right, so what we have here is, again, we can neglect air resistance and friction. So there will be no non-conservative work. So no energy losses. So we can apply the conservation of mechanical energy. Great. So what does our runaway truck ramp look like now? So we see that we have a ramp, and we can kind of draw this as a right triangle. Okay, and so this is a right triangle. It's going up this ramp. We have, the truck is going to go up, let's say, a distance L. We know what L is. L, we read, is 154 meters. The ramp is inclined at an angle theta. The angle theta is 14.0 degrees. Okay, we know that too. We can actually define where the truck starts. We can define this as the zero of potential energy. We are free to always do that. So where the truck enters a ramp, we can refer to that as the zero potential energy. We're always free to do that. And so we can call this y equals 0. And we're going to go at some sort of a height h. All right. Now, at the beginning where you have the ramp, what does the truck have? Well, it's going to have kinetic energy initial and potential energy initial at the beginning of the ramp. At the very top where it stops, it's going to have kinetic energy final and potential energy final. Right? That's what it's going to have. And so we look at this carefully. We know that kinetic energy initial, truck is going full speed. Kinetic energy initial is 1/2 m v naught squared. Again, v naught is what we're looking for. What is the initial speed? When the truck comes to a nice safe stop at the top of the ramp, we know that, fortunately for him, the kinetic energy final is going to be 0. Means the truck is at the top of the ramp, it's not moving. Now we're defining the zero potential energy at the bottom of the ramp. So potential energy initial, as defined by us, is 0. We call that y equals 0. The potential energy final is all a gain of gravitational potential energy, mgh. If the truck has a mass m and it goes up a height h. So again, total energy is entirely the same in both cases. You're literally converting all this kinetic energy to potential energy. All right, when you apply the conservation of energy. So that's what we're going to do now. We're going to apply the conservation of energy. Conservation of mechanical energy now. All right, so conservation of mechanical energy. So that means that kinetic energy initial plus potential energy initial is kinetic energy final plus potential energy final. Total energy, kinetic plus potential, must always be the same if you are allowed, if you can apply the conservation of mechanical energy. Now what's nice is that the potential energy initial we can call 0. I mean, that's 0. And the kinetic energy final, fortunately for this truck, is also 0. And so we can actually now do is say, well, the kinetic energy initial is 1/2 mv naught squared. And what's that equal? Mgh. And what's nice is I can cancel out the m's. And I don't know h, but I do know theta and L. So what's the relationship here? Well, I know that the sine of theta is h divided by L, right? It's the opposite over the hypotenuse. So I can actually write H as just L sine of theta, right? And so I'll stick that in there. All right, I'm just going to erase this stuff now for real estate purposes. All right, so I have 1/2. So I'm going to multiply through by 2. I have V naught squared is 2G. What's H? Oh, yes, it's L sine theta. Now I'll take the square root of both sides. So B naught is the square root of 2GL sine of theta. Plug in some numbers now. V naught at 9.80 meters per second squared. I'm going to erase this stuff now. We've made use of it. I'm just putting in final answer. Let's see. L, 154 meters. Sine of 14 degrees. Take the square root of all that. And I finally find that the truck was before, well, when it lost its brakes and went and got onto the runaway truck ramp, it was going at 27.0 meters per second. Okay, that was the initial speed of the truck before, as it entered the runaway truck ramp. Okay. I'm going to do one more conservation problem. I'm going to do Cutnell Johnson 6.53. All right. This one says, starting from rest, a 93 kilogram firefighter slides down a fire pole. The average frictional force exerted on him by the pole has a magnitude of 810 newtons. And his speed at the bottom of the pole is 3.4 meters per second. How far did he slide down the pole? All right, so now we're going to employ now a conservation of energy that's going to have to involve non-conservative work. Why? Because he's having a frictional force that's exerted on him of 810 newtons. So this problem is actually going to lose energy. Okay, so we have to employ the more general conservation of mechanical energy. All right, but the part that allows for non-conservative work. All right, so let's erase this. All right. So, as I just said, we'll have kinetic energy initial plus potential energy initial plus non-conservative work equals potential energy final plus kinetic energy final plus potential energy final. So again, we're going to have to add, because we're going to lose energy, we're going to have non-conservative work in here as well. So kinetic energy final plus potential energy final. All right. So now we know the firefighter starts from rest. As we're told in the problem. So V naught equals 0. And of course, kinetic energy initial is 0. If the firefighter is starting from rest, it means that he has no initial kinetic energy. Assume he slides down a pole of height h above the ground. That means that the potential energy initial will be mgh. But we define the ground as 0 potential. So we define the floor, if you will, or the ground. Find the ground floor or the bottom of the pole as the 0 of potential energy, which we can always do. So potential energy final is where the firefighter is at the bottom of the pole. That's going to be 0. All right. And kinetic energy final, that'll be 1/2 mv final squared. And of course, we know that V, we're told in this problem, is 3.4 meters per second. Here's all the information we know. So we can kind of simplify the problem now. Okay, so I'm going to use this information and simplify the problem a little bit. All right, and so we're going to take this equation, and there's a few things that go to 0. All right, and so we know the kinetic energy initial goes to 0 because of what I just said, because the firefighter starts from rest. We know the potential energy final is 0 because we've defined the bottom of the pole as 0. So potential energy initial, we're going to know that's mgh, m's the mass of the firefighter, plus the non-conservative work. I haven't done anything with that yet. And the final kinetic energy is 1/2 mv squared. All right. Now, the thing about it is, let's look at the non-conservative work. we are sliding down, he is sliding down a pole, and he's experiencing a frictional force F. That means we can think of the non-conservative work as a negative F, because negative means we're losing energy, times, and again, it's going against him, times the distance that he slid, h. Remember, force times a displacement is the work. He's sliding down a pole of a height h. He's losing this much energy. That energy is being dissipated. All right, so we can plug that in. And we say, okay, well, we know that mgh minus fh, again, F is the frictional force. We're told is 810 newtons. So it's pull on firefighter. Okay, and let's see here. Hang on one second. So if that's the case, and I'll plug it up here. So I have mgh plus minus fh equals 1/2 mv squared. And I want to find the height of the pole, right? So that's h. I can pull h out, factor it out. I get mg minus f is 1/2 mv squared. And finally, I can solve for h by dividing this factor on the bottom, and I get that h is equal to mv squared divided by 2 times the quantity mg minus h, or I'm sorry, mg minus f. All right. And now what's left to do is just plug in values, right? So I'm going to write some of this up here. I got my final equation, so let's plug it all in. So I know that h is the mass of the firefighter, 93 kilograms. His final velocity, 3.4 meters per second, quantity squared, divided entirely by 2. I'll put little brackets here. Let's see. Mass of the firefighter again, 93 kilograms. Acceleration of gravity is 9.80 meters per second squared. And again, I have the resistive frictional force of 810 newtons. Plugging it all together, doing that calculation, I will find out that the height of that pole is 5.3 meters. Okay, so the height of the pole that the firefighter slid down is 5.3 meters. Okay, the only thing I want to do now is discuss one more little concept. Okay, so we talked about work energy. So oftentimes you'll hear, we utilize, anybody who's paid an electric bill before, we know about power, right? So power has a particular definition in physics. It's the last topic of the chapter, power. Power is typically given by the letter capital P, and it is by definition the change in the work divided with respect to time. You can actually employ a calculus definition if you wish. In calculus, you would say it's dW dt. W is the work. How much work is delivered per unit time? I mean, that's what you're paying for when you pay your electric bill. You're being delivered a certain amount of work per unit time. Okay, and so so what's the units on this? Well, the units of power we have what? Joules per second. When you see joules per second together like that, work over time, we refer to that as a watt. So unit of power is the watt. Kilowatts, things like that. So you buy a certain amount of watt light bulb, 100-watt light bulb. Well, that means that it delivers 100 joules per second. Okay. All right. So now I'm going to do, and that's all there really is to that. I'm going to do 3 more problems, and then we'll call it a done deal. All right, here we go. I'm going to do OpenStax 7.27. Using energy considerations. And assuming negligible air resistance. Show that a rock thrown from a bridge (20.0 meters above water) with an initial speed of 15.0 meters per second, strikes the water with a speed of 24.8 meters per second. Independent of direction thrown. Okay, using energy considerations and assuming negligible air resistance means we're not going to have any losses, frictional losses. Show that a rock thrown from a bridge 20.0 meters above water with an initial speed of 15.0 meters per second strikes the water with a speed of 24.8 meters per second, independent of direction thrown. Okay, let me erase this and draw a little picture of what we're actually talking about. All right, so we have basically like the height of a bridge, and down here we have water. Okay, now we know that we can imagine that this is going to have a height h. And so the rock up here, it'll have a potential energy initial of mgh. It's also going to have an initial velocity. It's being thrown, right? So it's going to have a kinetic energy initial of 1/2 mv naught squared. Now it's going to hit the water. I'll define this as the zero potential energy. And I'm free to do that. So I'll define the water level as the zero potential energy. Totally okay to do that. All right, and so if I do that, then PE sub F is 0, and then kinetic energy final, well, that's just going to be whatever the final velocity is, 1/2 mv squared. All right, and so again, neglecting air resistance, we can employ the conservation of mechanical energy. Fantastic. So we then know that kinetic energy initial plus potential energy initial is kinetic energy final plus potential energy final. So again, we don't have to worry about direction at all. All we have to care about, again, we don't have to care about vector nature of anything. We just have to care about the speed. That's how you're independent of direction, by the way. All right, so potential energy final, that's 0. And so what do we have? 1/2 m v naught squared. V naught's the initial velocity. And initially it's way up here with a potential energy of mgh. And finally, it's going to speed up to a final velocity of v, 1/2 mv squared, the final velocity. And I have nothing for potential energy final. Now, one of the beauties here is I can actually cancel out all the m's. I don't care how heavy the rock is, it doesn't matter, as long as I'm neglecting air resistance. I'm going to erase this stuff now. And there's not much more to this problem. So don't care about so I'm looking for v. So I can multiply through by m. I have v squared is equal to v naught squared. And they're gonna already have this on their side, so plus 2gh. Very similar looking to something you get out of the kinematic equations. So again, v will be the square root of v naught squared plus 2gh. V would be the square root of, what did I say? It's going to be 15 meters per second is, again, I'm trying to verify, right? I'm trying to show that the final velocity is going to be 24.8 meters per second. That's what this problem is about. But anyway, 2 times 9.8 meters per second squared times, how high did we say it was? 20 meters. 20 meters above the water. Take the square root of all that. If you do all of this, you will find out that the final velocity will indeed be 24.8 meters per second. So check. Indeed, that's going to happen. And, and this nice here is that you actually could do this problem with kinematic equations if you so chose. But we also find out that it's interesting. We can actually do this via energy considerations and still get the right, we can get the right answer, just perfectly good, same right answer. There's an alternative way of doing it. All right, now let's go talk about power, do a couple power problems. All right. All right, I want to do OpenStax 7.33. Okay, what does it say? What is the cost? Do a little money problem here. What is the cost of operating a 3.00 watt electric clock? for a year. If the cost of electricity is $0.09, basically $0.0900 per kilowatt hour. Now, if you look at your electric bill, you'll notice that your energy is always given in your bill is always in how many kilowatt hours did I use? Well, what is a kilowatt hour? So let's look at this again. So we know by definition that the power is basically the work per time, right? And so what I could say, and the work is an energy, right? I could say that the work, I can cross multiply, it's really the power times the time. Kilowatt hour. When I write something like a power times the time, that's another fancy way of saying an energy. So kilowatt hour is a form of an energy. Okay, how much energy did you use? Okay, so I'm going to erase this up here. So again, we're looking at the cost of how much energy are we going to use in a year, and then how much is this going to cost us? So we know that this alarm clock, this electric clock, is basically burning 3.00 watts, 3 joules a second. Okay, and so we want to look at a total time of 1 year. So 1 year. But that doesn't do us any good. We need to put that into seconds, right? So we know there are 365 days in a year. Cancel out the years. Now we have days. And we know there's 24 hours in a day. Now we have hours. And finally, we know that there are 3,600 seconds per hour. So we're looking at a total time of a year. And so the equivalence in seconds for a year is about 3.15 times 10 to the 7th seconds. That's how many seconds are in a year. Okay, that's how long we want to consider. So we know that then if I take the W equals PT, which I just got done driving here, well, that's going to be 3.00 watts times this amount of time, T, 3.15 times 10 to the 7th seconds. Okay, so we're going to figure out how much that is in energy. So the work that the clock is going to do during that time will be 9.45 times 10 to the 7th joules. Now, what's a kilowatt hour? Well, 1 kilowatt hour, to put that in normal units, right? 1 kilowatt hour is going to be 1,000 watts times 3,600 seconds, right? We want to get into watt seconds, right? Which is basically joules. So kilowatt, it means 1,000 watts. An hour means 3,600 seconds. So a watt second is a joule, right? And that's going to be 3.60 times 10 to the 6 joules. And you can probably just look this up as well. If you want, if you want to see an energy unit of kilowatt hour, that's equivalent to 3.60 to 10 to the 6 joules. You can probably, there's certain books that have that as given as a conversion factor. All right, so what's this? So what is my power expenditure going to be in kilowatt hours? Well, let's see. It's going to be, how much power am I expending? 9.45 times 10 to the 7th joules. And a kilowatt hour, 1 kilowatt hour. Again, I'm going to use convert this as a conversion now, per 3.60 times 10 to the 6 joules. And I find out that the power that we're actually that's being expended by this electric clock is going to be 26.25 kilowatt hours. So all the kilowatt hours that you use, the electric clock in a given year is going to take 26.25 of those. All right, well, finally, how much is that going to cost you? All right, so I'm going to erase some of this up here. So to operate that clock for a year, how much money is this going to cost? So we know that the cost is what? It's going to be 9 cents. 0.0900 dollars per kilowatt hour. That's how much, that's your rate for what you're paying for your electricity. Multiplied by what? For an entire year, you're going to spend 26.25 kilowatt hours to operate that electric clock. So it's going to cost you a whopping $2.36. So not even a cup of coffee at Starbucks to operate your electric clock for an entire year at this rate. Okay, so not too bad. I think you can keep the clock on. All right, last problem. Now we're going to talk about a more painful electric bill. So I'm going to erase this. It's going to be more like a summer, well, not quite a summertime air conditioning bill, but I mean, at least in Texas, they're pretty big. All right, so last problem of the video, OpenStax 7.34. Let's talk about one that's more painful. A large household air conditioner. So I can stop right there. Already painful, right? So a large household air conditioner. May consume 15.0 kilowatts of power. Okay, pretty bad. What is the cost of operating the air conditioner? For 30.0 days. I'm sorry. For operating air conditioner 3 hours per day. So 3 hours, 3.00 hours per day. For 30.0 days. If the cost of electricity is $0.110, 11 cents basically, per kilowatt hour. All right, so this one's going to be more to the point. So it is summertime. Oh, a large household air conditioner may consume 15.0 kilowatts of power. What is the cost of operating the air conditioner? 3.00 hours per day for 30.0 days if the cost of electricity is $0.110 per kilowatt hour. All right, so again, this is going to kind of hinge upon the last problem we did, so I'm going to erase this now. Okay, so what do we know? Again, the definition of power in this case will just be the work divided by the time. All right, and so again, we would say that I can solve for the work, and this is basically the power times the time. Okay, pretty simple. How much time now? So again, the time is going to be 3 hours per day times 30 days. That'll give you hours, and that'll give you 90.0 hours. But again, we want to convert to seconds. So one more factor, this will give us hours, days will cancel, and there's 3,600 seconds in an hour. Hours cancel. So again, the total time in seconds operating this air conditioner for the 30-day period will be 3.24 times 10 to the 5th second. That's how long it's going to operate, okay? Now, we're ready to calculate the total work. So to work, we know what the power consumption is. It's 15 kilowatt hours, or 15 kilowatts. Compared to the problem, that's 15 times 10 to the 3rd watts times 3.24 times 10 to the 5th seconds. Okay, that'll give us joules. So work, total work being done by this air conditioner will be 4.86 times 10 to the 9th joules, 4.86 billion joules. Now, in the last problem, I'm going to erase some of this stuff now. So this is what we have. In the last problem, we derived a conversion factor to get to kilowatt hours. Remember in the last problem, so in previous problem, we found that 1 kilowatt hour is 3.60 times 10 to the 6th joules. All right. Well, we know how much we're burning, so we know that the work will be in kilowatt hours will be 4.86 times 10 to the 9th joules. And the conversion to kilowatt hours, we can figure out the cost. 1 kilowatt hour per 3.60 times 10 to the 6th joules. Doing that conversion gives me, in kilowatt hours, 1,350 kilowatt hours. So again, that's how much the air conditioning is using in kilowatt hours. And again, this is an energy term. And now we can go to the final. We know how much electricity cost us. Cost is equal to 0.110 dollars per kilowatt hour, multiplied by how many kilowatt hours that I burned. 1,350 kilowatt hours. Now I get dollars. So finally, my cost is going to be $148.50. Now that's a little bit more of a not so good electric bill. I mean, Texas, they get up to around $300 or $350. So that's what my bill ends up being. So anyway, that is it for this particular chapter. And and that is a finalization of chapter 6 on energy. All right, so thank you very much.